All right, let's start looking at amines. We'll start with the normal stuff. Call primary amine, secondary amine, tertiary amine. Note this is different than alcohols and alkyl halides, where you look at the carbon that the Cl is bonded to, or the carbon that the OH is bonded to for alkyl halides and alcohols, to see if it's primary, secondary, tertiary. Here we look at the nitrogen itself. How many groups are coming off the nitrogen? One group is primary, 3 groups bonded to the nitrogen, 3R groups is tertiary. Something you might not have considered a question. When we look at the geometry of amines, we note that nitrogen's almost, for a neutral amine, is going to have 3 groups coming off of it. Could be hydrogens, but it'll also have a lone pair given a trigonal pyramidal geometry. Isn't that chiral, though? When you count the lone pair, isn't that 4 groups coming off of that central nitrogen? Yes, it is. Technically, amines can be chiral. However, this little equilibrium here to just invert, this little inversion of stereochemistry to go from this orientation to this orientation, its mirror image, is just really, really rapid. There's no real energy barrier to stop this flipping happening. So if you were to make a chiral amine, you would find it would be a racemic mixture of the 2 of them consistently. You cannot have a chiral amine. It will not stay as a chiral compound. It's always flipping back and forth. So long story short, we just don't worry about it. However, if you have ammonium salts, note if you add a 4th group to the nitrogen, 1, 2, 3, 4, then you're not going to get flipping around because it's not a lone pair. It's this lone pair that can flip back and forth so easily. Without a lone pair, you're not going to get flipping. Then you can have chiral ammonium salts. Okay, let's look at the nomenclature of amines. And IUPAC, always look at the longest carbon-carbon chain and then add amine to it. Common, you look at the alkyl group on the nitrogen. So very similar to naming alkyl halides and whatnot. So CH3NH2, according to IUPAC, would be methanamine because CH3 is the methane, 1 carbon methane, so it's methanamine. That's IUPAC. The common name, it's like, well, this is the amine, this is a methyl group on the amine, so this is methylamine. Most of the time, for small molecules, we tend to use the common name. Most people call that methylamine. All right. The deal is when you have different groups coming off the nitrogen, you have to make sure in the name that there's no confusion as to where those groups are. And so with these compounds, you often will see this capital N there to indicate what is coming off the nitrogen, because for the IUPAC name, we've got this 6-membered ring here, so this is a cyclohexane. There's an amine on it, so it's cyclohexanamine. But it's got a methyl and an ethyl. You have to indicate that the methyl and the ethyl are coming off the nitrogen, because if you just say methyl cyclohexanamine, you might think that the methyl's on the cyclohexane. So this would be N-ethyl N-methyl cyclohexanamine. Cyclohexanamine because the cyclohexane is the largest group. Ethyl before methyl because of alphabetical, and you put the N's in front. Okay. And if you're looking at the IUPAC name, would be the common name would be N-ethyl N-methyl cyclohexylamine, because this is a group. These are 2 groups, 3 groups: the ethyl group, the methyl group, the cyclohexyl group coming off that amine. When you get into cyclic amines, note we have some special names here. We've looked at this before. NH2 on a benzene ring is aniline. If you have the nitrogen in the middle of the ring, you've replaced one of the carbons of benzene with a nitrogen. This is pyridine. If you've got a 5-membered ring with 2 double bonds and a nitrogen there, this is pyrrole. Recall from earlier, this lone pair is part of the aromatic system. This is an sp2 hybridized nitrogen with these 2 electrons in an unhybridized p orbital. Pyrrole is aromatic. If you have looks like a cyclohexane, but you take off one of the carbons, put it in the nitrogen instead, this says piperidine, and this is pyrrolidine. All right. Your basic physical properties and whatnots of amines, yes, similar to alcohols, but not quite as strong. So they've got higher boiling points than alkanes because we can get some hydrogen bonding, but not quite as high as alcohols because the hydrogen bonding for N and H isn't as strong as O and H. All right, solubility, yes, amine is a polar group, so soluble in water if 5 carbons or less on the chain. And spectroscopy, we all know about the IR and the NMR of these guys. Note for NMR that this hydrogen bonded to nitrogen tends to go between 0.5 and 5 ppm, but I've seen it all over the place. And it tends to be broad with no splitting. All right. Now here's the thing about amines. In general, all amines smell bad. You know, ammonia, if you're familiar with ammonia, it's not the most pleasant of smells. A lot of amines smell bad. Pyridine, I work with pyridine quite a bit. Man, that stuff stinks. You know, it's the type of stuff you get a drop of pyridine on your hand and your hands stink for 3 days because it's just got to wear off. It's just nasty. But here's some other interesting amines that we'll go through. All right, so if you take trimethylamine, nitrogen with 3 CH3s on it, this is a smell of rotting fish. Lovely flavor there. All right, if you take an NH2 and amine and put in 5 CH2s and then another NH2, this is cadaverine. This is the smell people give off when they die. This is the molecule that fish give off when they die. This is a molecule that people give off when they die. If there were 4 CH2s, that would be putrescine. I'm not sure exactly what it smells like, but it's not good. All right. Other amine compounds, urine, bad breath, all this nice stuff. Ugh, amines, stinky. All right. Alkaloids are amines from plants. And we note all amines like ammonia are slightly basic. So amines from plants are bitter, and they have names that end in INE because they are amines, such as morphine, cocaine, or as we say cocaine, nicotine, caffeine. All of these are amines, and that's why caffeine is spelled really weird and stuff like that. Note that alkaloids, a number of these amines from plants, tend to affect the brain quite a bit. All right. And here's another one, this histamine right here. You got the amine on here. It's a vasodilator. Most people are allergic to it. Your body actually, when you have an allergic reaction, your body creates histamine, and that causes redness and swelling, hives and whatnot. And so if you are having an allergic reaction to something because your body's creating this histamine, you need to take an antihistamine. All right. Now, when we're looking at the preparation of amines, most people would think, and rightly so, that a nice SN2 reaction would occur. I mean, if you've got ammonia and you've got RX, you've got an alkyl group with a decent leaving group, just a simple SN2, because we know that NH3 is a respectable nucleophile. It will attack the carbon, do an SN2 reaction, and put that nitrogen on the R group. And then recall at the end of a substitution reaction, if your product has a nitrogen or oxygen that is positively charged and has hydrogens on it, you get a deprotonation reaction. Another amine will come in here, take that hydrogen, and you just get RNH2 plus NH4 plus your alkyl halide. And that's fine. And that works, but something we're going to find out in just a little bit, that the more R groups you have on the nitrogen of the amine, the more substituted the amine is, the more basic it is. Yes. Okay, recall that R groups are slightly electron donating. So an R group is going to donate a little electron density to this nitrogen, which means that lone pair of electrons is a little bit more nucleophilic now that that R group is on there. What this means is that if you were to run this reaction, And as this reaction is running, you start with ammonia to make this primary amine, and you're hoping, oh, I just want to end with this primary amine. You won't, because as this stuff, as the primary amine starts to get made, it's a stronger nucleophile than your original ammonia. So as we start generating more of this primary amine, it will react with Rx to make the secondary amine. Well, now that secondary amine has 2 R groups on it, so it's more nucleophilic, it's more basic than this even was. So then the secondary amine is going to react with your Rx. Long story short, there's pretty much nothing you can do experimentally to stop from making a mess. Because at the end of the day, all of your Rx will be used up. You're going to have leftover ammonia, you're going to have leftover primary amine, you're going to have leftover secondary amine, and you're going to have tertiary amine, all mixed in there. So your yields will be very, very low, and you've got a whole lot of cleaning up to do to separate which product you wanted from there. Yeah, the polyalkylations is just going to happen. So what if you want a primary amine then? How, if you have ammonia, which is nice and cheap, and you want a primary amine, this should be an easy reaction. It's not. How do you do it? Well, along comes Gabriel, the Gabriel synthesis of primary amines. And what Gabriel did was he said, okay, let me take this molecule, phthalimide. This hydrogen here has a pKa of 10 because it's on this nitrogen, but it's between 2 carbonyl groups, and we've known that tends to lower the basicity of hydrogens or increase the acidity of hydrogens, lower the pKa's. And with a pKa of 10, if you react phthalimide with hydroxide here, we can easily take off that hydrogen to make this beast right here, that negatively charged beast. It turns out this negatively charged beast in an SN2 mechanism does a really good job of substituting for hydroxide. Recall, hydroxide normally a very poor leaving group. However, in the presence of a deprotonated phthalimide, a deprotonated phthalimide will react with an alcohol, a primary alcohol, in an SN2 fashion and kick off that hydroxide. And part of the reason is because with that hydroxide that got kicked off, we're in aqueous solution, you're going to generate this amine and you're going to generate this dicarboxylate. Yeah, okay, this is just base catalyzed, well, what do you call it? When you've got a molecule and you break it apart with water. What do you call that? Hydrolysis. That's correct. All right, base catalyzed hydrolysis of this amide, because that's what it is. Carbonyl N, this is phthalimides, a special amide. So just do base catalyzed hydrolysis, which makes these carboxylates, which are pretty darn stable. And so that's one of the driving forces of this reaction is these carboxylates are fairly stable molecules. All right, but this will then give you this amine without your polyalkylations, because once you've got this product here, this is just a plain old amine. It is not powerful enough to do the SN2 reaction and kick off the hydroxide. Only this deprotonated phthalimide is. So when you make this product, it's not going to act as a nucleophile for a primary alcohol, so you just generate this product, your primary amine. Way to go, Gabriel. Okay. And here's some other stuff we know, so it's review. If you've got a nitro group, H2 palladium on carbon, or you could use H2 with iron and HCl, or H2 with tin and HCl, that will reduce a nitro group to NH2, reduce a nitro group to an amine. And if you have a nitrile, you can react it with lithium aluminum hydride followed by water. Recall that generates an amine. The carbon of the nitrile becomes CH2. Note, lithium aluminum hydride with nitriles adds 2 H2 molecules across the double bond. H2 across, another H2 across to make CH2 and H2. And if you have an amide you can add lithium aluminum hydride and water and also generate the amine. Recall that this reaction goes through the amide step. Okay. The last way that we're going to talk about making amines is reductive amination. And reductive amination is kind of cool. The nice thing about it, it has a specific reagent. So as soon as you see this reagent, you're like, aha, reductive amination. And now I know exactly what to do here. If you have an aldehyde or a ketone and you react it with ammonia, you will form the imine. We learned that in chapter 21. Then if you reduce the imine, you will get the amine. So reductive amination is a way of taking an aldehyde or ketone and converting it into an amine. And it turns out the best reducing agent for the reduction, this step here, is NaBH3CN. Remember, NaBH4 is sodium borohydride. This is sodium cyanoborohydride. So, if you're looking at on an exam or something like that and you say, oh, okay, I've got an aldehyde or ketone, I have an amine, and I see sodium cyanoborohydride, boom, reductive amination, I am turning this carbon into a CH2, and I'm adding an amine on there also. So this carbon becomes a CH2, and your amine here, this is methylamine, gets added to that CH2. Reductive amination with sodium cyanoborohydride.